When sizing a neutral conductor in a three-phase delta system, it's crucial to adhere to the National Electrical Code, specifically sections 250.66 and 250.24 bone. These sections outline the requirements for neutral conductor ampacity, ensuring safety and proper system function. Let's break down the process step by step. Firstly, according to NEC 250.66, for a three-phase delta system, the neutral conductor must have an ampacity no less than 50% of the ampacity of the ungrounded conductors. This provision establishes a baseline for the neutral conductor size, taking into account the overall system capacity. Secondly, to apply this to a practical example, consider a scenario where 4/0 conductors are used. These conductors typically have an ampacity of 350 amps. Following the 50% rule, the neutral conductor must have an ampacity of at least 175 amps, which is half of 350 amps. However, this is not the only requirement to consider. Thirdly, NEC 250.24 bone introduces another factor. This section stipulates that if the neutral conductor carries the normal load current of an unbalanced three-phase, four-wire system, its ampacity must be no less than the ampacity of the ungrounded conductors. This means that if there's a significant neutral load, the neutral conductor must be sized accordingly. Now let's consider a situation with a possible neutral load of 85 amps. Since 85 amps exceeds the 50% minimum ampacity requirement calculated earlier at 175 amps, the neutral conductor must be sized to carry at least 85 amps. In summary, the neutral conductor must be sized for a minimum of 85 amps in this specific scenario. In addition to these considerations, there are other factors that can affect the selection of the neutral conductor. One such factor is the type of load that the system will be serving. If the system will be serving a large number of nonlinear loads such as electronic ballasts or variable frequency drives, the neutral conductor may need to be oversized to account for the harmonic currents that these loads can generate. Harmonic currents are currents that are at frequencies that are multiples of the fundamental frequency of the power system. These currents can cause a number of problems, including overheating of the neutral conductor, increased voltage drop, and interference with other equipment. To mitigate these problems, it is important to ensure that the neutral conductor is sized large enough to carry the harmonic currents. Another factor that can affect the selection of the neutral conductor is the length of the conductor run. The longer the conductor run, the greater the voltage drop will be. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to the resistance of the conductor. Excessive voltage drop can cause a number of problems, including reduced performance of equipment, increased energy consumption, and premature failure of equipment. To minimize voltage drop, it is important to use a conductor that is large enough for the length of the run. The NEC provides tables that can be used to determine the minimum size of conductor required for a given length of run and load current. In addition to these factors, it is also important to consider the ambient temperature in which the conductor will be installed. The ampacity of a conductor is reduced as the ambient temperature increases. This is because the higher temperature increases the resistance of the conductor, which in turn increases the amount of heat that the conductor generates. If the conductor is not sized properly, it can overheat and fail. The NEC provides tables that can be used to determine the ampacity of a conductor at different ambient temperatures. When selecting a neutral conductor, it is important to consider all of these factors to ensure that the conductor is properly sized for the application. Using a conductor that is too small can result in a number of problems, including overheating, voltage drop, and premature failure. Using a conductor that is too large is not necessarily a safety hazard, but it can be more expensive than necessary. Therefore, it is important to carefully consider all of the factors involved before selecting a neutral conductor. Now, let's delve deeper into the specific requirements of NEC 250.66 and 250.24 bone to gain a clear understanding of their implications. NEC 250.66 primarily addresses the sizing of grounding electrode conductors and bonding jumpers. However, it also contains provisions for sizing the neutral conductor in certain circumstances. Specifically, it states that in a three-phase delta system, the neutral conductor must have an ampacity of not less than 50% of the ampacity of the ungrounded conductors. This requirement is intended to ensure that the neutral conductor is capable of carrying the unbalanced current that may flow in a three-phase delta system. In a perfectly balanced three-phase system, the current in each of the three phases is equal, and the neutral current is zero. However, in reality, most three-phase systems are not perfectly balanced. This means that the current in each of the three phases is not equal, and a neutral current will flow. The amount of neutral current that flows will depend on the degree of imbalance in the system. The more unbalanced the system is, the greater the neutral current will be. NEC 250.66 requires that the neutral conductor be sized to carry at least 50% of the ampacity of the ungrounded conductors. This is to ensure that the neutral conductor is capable of carrying the maximum neutral current that may flow in the system. However, NEC 250.24 bone provides an exception to this rule. This section states that if the neutral conductor carries the normal load current of an unbalanced three-phase, four-wire system, its ampacity must be no less than the ampacity of the ungrounded conductors. This exception applies to situations where the neutral conductor is used to carry the current from single-phase loads that are connected between one of the phase conductors and the neutral conductor. In these situations, the neutral conductor must be sized to carry the full current of the single-phase loads. For example, suppose a three-phase delta system has a neutral load of 85 amps. This means that there are single-phase loads connected between one of the phase conductors and the neutral conductor that draw a total of 85 amps. In this case, NEC 250.24 bone requires that the neutral conductor be sized to carry at least 85 amps. This is because the neutral conductor must be capable of carrying the full current of the single-phase loads. In summary, NEC 250.66 requires that the neutral conductor in a three-phase delta system have an ampacity of not less than 50% of the ampacity of the ungrounded conductors. However, NEC 250.24 bone provides an exception to this rule. This section states that if the neutral conductor carries the normal load current of an unbalanced three-phase, four-wire system, its ampacity must be no less than the ampacity of the ungrounded conductors. The choice between these two requirements depends on the specific circumstances of the installation. If the system is a balanced three-phase system with no single-phase loads connected to the neutral conductor, then NEC 250.66 applies, and the neutral conductor must have an ampacity of not less than 50% of the ampacity of the ungrounded conductors. However, if the system is an unbalanced three-phase system with single-phase loads connected to the neutral conductor, then NEC 250.24 bone applies, and the neutral conductor must have an ampacity of not less than the ampacity of the ungrounded conductors. In addition to these code requirements, it is also important to consider the practical aspects of sizing the neutral conductor. For example, it is generally a good idea to oversize the neutral conductor slightly to account for future load growth. It is also important to consider the voltage drop in the neutral conductor. If the voltage drop is too high, it can cause problems with the operation of equipment that is connected to the neutral conductor. Finally, it is important to ensure that the neutral conductor is properly grounded. Grounding the neutral conductor helps to protect people from electric shock and to prevent damage to equipment. By carefully considering all of these factors, it is possible to select a neutral conductor that is properly sized for the application and that will provide safe and reliable operation. Furthermore, let's explore some additional considerations and best practices for ensuring accurate and compliant neutral conductor sizing. Firstly, always consult the latest edition of the NEC. The electrical codes are updated periodically to reflect new technologies, safety standards, and best practices. Using the most current edition ensures your installations meet the latest requirements. Secondly, perform a thorough load calculation. Accurately determining the expected load in the neutral conductor is critical. This includes accounting for both linear and nonlinear loads, as well as any potential future load growth. Overlooking load requirements can lead to undersized conductors and potential safety hazards. Thirdly, consider the impact of harmonic currents. Nonlinear loads, such as variable frequency drives and electronic lighting ballasts, can generate harmonic currents that flow in the neutral conductor. These currents can cause overheating and other problems if the neutral conductor is not properly sized. Use appropriate methods and equipment to measure and mitigate harmonic currents. Fourthly, account for voltage drop. Excessive voltage drop in the neutral conductor can negatively impact the performance of equipment and increase energy consumption. Use appropriate conductor sizing and voltage drop calculations to ensure that the voltage at the load is within acceptable limits. Fifthly, ensure proper grounding and bonding. Grounding and bonding are essential for electrical safety. Proper grounding and bonding of the neutral conductor helps to protect people from electric shock and prevent damage to equipment. Follow the NEC requirements for grounding and bonding to ensure a safe and reliable installation. Sixthly, use appropriately rated equipment. Ensure that all equipment, including conductors, connectors, and overcurrent protection devices, is rated for the intended application. Using undersized or improperly rated equipment can lead to overheating, failure, and potential safety hazards. Seventhly, document all calculations and decisions. Maintain detailed records of all load calculations, conductor sizing decisions, and other relevant information. This documentation can be helpful for future reference troubleshooting and inspections. Eighthly, seek expert advice when needed. If you are unsure about any aspect of neutral conductor sizing or electrical installations, consult with a qualified electrical engineer or electrician. They can provide valuable insights and guidance to ensure a safe and compliant installation. Ninthly, conduct regular inspections and maintenance. Regularly inspect electrical installations to identify any potential problems, such as loose connections, damaged conductors, or overloaded circuits. Perform necessary maintenance to keep the system in good working condition and prevent failures. 10thly, stay informed about industry best practices. Attend industry conferences, read trade publications, and participate in continuing education courses to stay informed about the latest developments in electrical safety and best practices. Continuous learning is essential for maintaining competence and ensuring safe and compliant installations. By following these additional considerations and best practices, you can ensure that your neutral conductor sizing is accurate, compliant, and safe. Remember that electrical safety is paramount, and it is always better to err on the side of caution. If in doubt, consult with a qualified professional. To further illustrate the application of these principles, let's consider a more complex scenario. Suppose you are designing the electrical system for a commercial building that includes a mix of lighting, HVAC equipment, and computer loads. The building will be served by a 480 volt/277 volts, 3-phase, 4-wire system. To properly size the neutral conductor, you would need to follow these steps. Firstly, perform a detailed load calculation for all the electrical equipment in the building. This would include determining the total connected load for lighting, HVAC, computers, and any other equipment that will be served by the system. Secondly, determine the expected load on the neutral conductor. This would involve analyzing the load distribution across the 3 phases and identifying any unbalanced loads that will contribute to neutral current. For example, single-phase lighting loads connected between phase and neutral will contribute directly to neutral current. Thirdly, calculate the minimum required ampacity of the neutral conductor based on NEC 250.66 and 250.24 Bohm. As discussed earlier, NEC 250.66 requires that the neutral conductor have an ampacity of not less than 50% of the ampacity of the ungrounded conductors. However, NEC 250.24 Bohm requires that the neutral conductor have an ampacity not less than the maximum unbalanced load served by the neutral. Fourthly, consider the impact of harmonic currents. Since the building will include computer loads and potentially electronic lighting ballasts, it is important to account for harmonic currents in the neutral conductor. Use appropriate methods and equipment to measure and mitigate harmonic currents. This may involve oversizing the neutral conductor or using harmonic filters. Fifthly, account for voltage drop. Calculate the voltage drop in the neutral conductor to ensure that the voltage at the loads is within acceptable limits. Use appropriate conductor sizing and voltage drop calculations to minimize voltage drop. Sixthly, select a neutral conductor that is appropriately sized for the application. The selected conductor must have an ampacity that is equal to or greater than the calculated minimum ampacity, and it must be suitable for the environmental conditions in which it will be installed. Seventhly, ensure proper grounding and bonding. Ground the neutral conductor in accordance with NEC requirements to ensure electrical safety. Eighthly, document all calculations and decisions. Maintain detailed records of all load calculations, conductor sizing decisions, and other relevant information. This documentation can be helpful for future reference, troubleshooting, and inspections. By following these steps, you can ensure that the neutral conductor is properly sized for the commercial building, providing a safe and reliable electrical system. Remember that electrical design and installation can be complex, and it is always best to consult with a qualified electrical engineer or electrician if you have any questions or concerns. And finally, it's essential to remember that local codes and regulations may have additional requirements beyond the NEC. Always check with your local authority having jurisdiction to ensure full compliance.